All right, good afternoon, or good morning, or good night, depending on when you're watching this if you're not catching it live. Reminder of due dates. We will finish 5.7 today, which means it will be due in a week. I haven't set that due date up, but I'll set it up as soon as this class is over. So that'll be 10/7. We likely will not finish section 8 today. We will likely finish it in next class, which means it would be due 1 week later. So in regards to that, our first test is going to cover section 5.1 through 5.8, 8 sections for the first test. So assuming we finish 5.8 on Monday, which is October the 5th, then our test date traditionally would be October the 12th, a week later. I don't want to say definitively yet, so you're still seeing most likely, but I really don't see a scenario in which this isn't what ends up happening. So your first test is likely going to run 2 days, the 12th and the 13th. Your test will be located in my math lab in the quiz and test section, naturally. It will be marked something along the lines of test 1, chapter 5. I do not know how many questions I'm going to make it yet, but you will have 90 minutes to take it. Somewhere in the ballpark of 20, 25 questions. Some of the questions are usually pretty short for these, like what is the sine of 30 degrees? You can answer that in 3 seconds if you really know your stuff. So you'll have some shorter questions, but you'll also have some longer questions, maybe an application or two, which means word problems, but not a ton of them. You'll have 2 full days to attempt this, so you don't have to take it during regular class time. We will still have regular class during regular class time. So you could take the test later that day, or you could take it the next day, but just those 2 days, that's it. I think that's a pretty good window. I think that's acceptable. And then just like all homework problems, they're due by 11:59 p.m. the night of probably the 13th. You will have to show your work. There will be a location in Canvas for you to submit that to. I know we don't use Canvas a lot for this course, but when you log into Canvas, it will be one of the only things you'll see. You'll have a tab that says submit test 1 work here. Absolutely do not email me your work. Emailed work will not be looked over. I need all of this stuff in one location, so I'm not trying, well, when did Bob send that email? Was it 3 weeks ago? Was it 4 weeks ago? Where was that email? I get 40 to 100 emails every day, depending on the day. So please do not email me your work because I will not look at it if you email it to me. You can take a picture with your cell phone if you have access to a scanner. You could scan your work that way, but just so I make sure you're not going off and doing anything weird, you do have to submit your work in Canvas within 15 minutes of finishing the test. So my math lab has a timestamp when you finish. Canvas has a timestamp when you submit that. If more than 15 minutes passes, and if it's 16 minutes, I think you probably know me enough at this point, I'd hope, to understand that that's fine. But if it's 30 minutes, I don't know. That's where we're getting into the, I don't really like that side of things. If it's 24 hours later, your test has just been negated. I'm not even going to accept it anymore. You have to submit your work. You must submit your work. If you don't submit work, I will go back and my math lab test grade that it gives you will now be a 0. There is no way that anyone's doing this test without having written down one thing at least and making an A or a B on it. An F, okay, maybe, probably. But if I see a student's got like a 98 on the test and I go back and I look for their work and I don't see a submission, I'm going to go, well, nope, that doesn't count anymore. So this is super serious. For now, I'm not going to make you put your cell phone up and record yourself taking the test. We're trying to keep this simple. Remember that the important aspect of this course is that you actually learn this information because you're probably going to calculus next, where this stuff is going to be important, where you're going to be using this stuff, pun intended, periodically. It's not the only thing you do in calculus, but you do calculus with trigonometry quite frequently. So please understand, if you're in this course, you're probably going to calculus next, and that means you can't just forget this stuff. So you trying to cheat the system in any way, shape, or form in here is going to hurt you twice as hard in calculus. Because in calculus, your teacher's going to go, well, you were supposed to learn that last class. Why didn't you? I'm not here to teach you trig. I'm here to teach you calculus. Okay. I will be giving you a thorough review assignment located in the homework that will be comparable to the test. While this will not hurt or help your grade, this grade will not affect your homework grade in any way, shape, or form. Now, it might say it in my math lab, but don't worry about that, or don't think it's going to help you. Do it anyways, because the test and the review will be comparable to each other. If you can do the review well, you can do the test well, as long as you don't panic. So I will show this information again when it becomes more relevant over the next several classes. If you don't submit this test in time, please understand that you are getting a 0 on the test. You have got to submit the test during one of these 2 days. If you come to me a week later, Mr. Beckner, I didn't take the test. If you don't have a doctor's note for me saying that you were going through something, then I'm not going to give any kind of extensions. I'm not going to give any kind of redos. So make sure you take this test. Test 1 of this class is extremely important, and here's the reason. You literally can't do anything in test 2 or test 3's material without having mastered almost everything from test 1. I said almost everything. You don't have to master the graphs, honestly. The inverse trig stuff, while it's important, it doesn't pop up nearly as much as everything else. But if you can't tell me what the sine of 30 degrees is, if you can't tell me what the cosine of 90 degrees is, if you can't tell me the Pythagorean identity and the tangent sine over cosine, all of those things, especially like the things on the little board cheat sheet, you're going to have a bad time in the rest of this course. Everything in chapter 5 is like 1 + 1 for the rest of this course. So if you do bad on test 1, you need to get your act together very, very, very quickly, because that material will not go away. In fact, it's only going to build on it and get more difficult and expand the ideas and concepts. I think I've tried to relate, and I think I do it pretty well, that trigonometry is really only like 4 or 5 basic ideas, and they just keep, pun intended, circling around each other. We'll introduce a new formula, we'll introduce a new concept, we'll do this backwards, we'll do this forwards. But everything ties together just in such a complete package. So I'm going to say this one more time. Chapter 5, if you can't handle it, you're not going to be able to handle the rest of this course. So you have got to put in 5 times as much effort right now if you're struggling. And usually it's time that people just aren't willing to commit. Remember, 6 hours a week for homework for this class at a minimum. If you're doing any less and you're not understanding the material, that is on your end for now. Okay, so that stuff aside, let's kind of reiterate where we were in 5.7. Inverse trig functions. So we related the idea of an inverse function and it being an invertible function that it had to pass the horizontal line test. And that enabled us to build our inverse trig functions. Remember, these are not being raised to the -1. This is not 1 over sine x. And if I didn't say that last time, make sure you understand that. This is not 1 over sine x. This is inverse sine x. I know it looks just like it would be 1 over sine x. 1 over sine x would look like this. Go. Stop that. Thank you. Oops. This would be 1 over sine x. It would have to have parentheses around the trig function and the -1 that way. With the -1 here, that is what denotes that it's an inverse function, not a reciprocal. So there's a giant distinction between those two things. So in fact, sine of x raised to the -1, which is 1 over sine x, is actually the same thing as cosecant. So sine x raised to the -1 in this manner is cosecant. Sine x with a -1 in the middle sandwiched like that has nothing to do with any of that cosecant jazz. It's saying we're swapping the idea of what's the x's and what's the y's. So we also discussed how we had to really, really limit the window of your sines and cosines because of how they are. They wave around like this. So to pass the horizontal line test, it's going to fail miserably in this way. So we had to trim it down immensely. And we ended up having to trim it down from -π/2 to π/2 in terms of x, or the domain of the regular function, which means the range ended up being -π/2 to π/2. Whereas the range of the regular function being -1 to 1, now the domain of the inverse function is -1 to 1. We took that same idea and spun it for the cosine, showing that we had to actually restrict it from 0 to pi. I know it's annoying that these trig functions, they always have these subtle differences between them. Sine and cosine waves look almost identical in the grand scheme of things, but one of them starts at a height of the amplitude, the other starts at 0. One of them, when you invert them, you have to do it this way. One of them, when you invert it, you have to do it this way. And again, that's just to make sure that you're not bumping into it more than once with their horizontal lines. There we go. We showed the graphs of the inverse functions. We explained kind of the reasoning as to why they loop around in opposite directions, because remember, in inverse function, the idea is you're swapping x and y coordinates. Bigger picture, it means you're reflecting across the line y equals x. So if you put, let's just do the sine function. Here's your sine of x. Then, if we flip that about the line y equals x, what we get is this. And I drew that terribly. In fact, the blue line is what's drawn terribly. So let me just do that a little better. Almost looks like a DNA strand, but only part of one. And that's that. So regular function, you can find the inverse function by just treating this y equals x line as a mirror. Nobody really does it that way, though. We just say swap the x and y coordinates because that's a much easier concept. But that proves that the bending should be this way, whereas last time I just kind of argued reasons. Now I visually showed it. I did mention that I'm not really going to test you on the pictures of the inverse sine and inverse cosine functions. This does come up in calculus, though, so I'm not saying you'll never see this again. You will see this again at some point. But we don't deal with it too much in regular trig. So what we spent time doing is finding inverse sines of something. Now remember, when you're an inverse sine for a sine of something, it's sine of an angle ends up equaling the opposite over the hypotenuse, or if it's cosine, adjacent over hypotenuse, etc. So the inside was the angle, and then this right side is your ratio. But when we have inverse sine of something, the inside of this is supposed to be the opposite and hypotenuse, and then what it equals would be the angle. These are flip-flopped. So we said, okay, this black inverse sine of square root of 2 over 2 is really just saying the same thing as this. Find an angle such that the sine of the angle is square root of 2 over 2. Some people will do this rewrite, some people will not. That's up to you and how much practice you do and how much you feel you need it. But remember, these inverse trig functions have massive restrictions. The inverse sine is restricted between quadrants 1 and 4 because this goes from negative pi over 2 to pi over 2. And we talked about how you can't even use angles like 3 pi over 2 or 11 pi over 6 because that's not in this actual window. Those would be up here in relation to this graph. So we had to turn them into, instead, rotate clockwise and get negative angles. That's not going to be an issue for the inverse cosine because inverse cosine goes between 0 and pi, which is in quadrant 1 and 2. So they both have their complications. They both have little details you're going to have to memorize. This red ink was me saying back in 5.2 or 5.3 before we talked about inverse trig functions, this is what I would have asked, where you find all the different angles and you'd end up with 2 answers. But these inverse trig functions, they generally are only going to have 1 answer unless it's something weird or wacky that, spoiler alert, won't happen on the first test or the first series of homeworks. We did another one. The first one we had to use a right triangle. The second one we ended up using the quadrantals. The third one was more similar to the first one. Yeah. So now let's do more. D. And in fact, let me give myself just a little more space. Oh, I'll just go to the next page then. And this is, oh, did I not make that memo? I said it, but I didn't type it, did I? Okay, so the memo related to C first. Let me just copy paste that. Much later. I can delete it. Sorry about that. We did D last class? Well, why isn't it? Oh, you know what happened? Yeah, I don't know if anyone remembers. I do now. I was having problems with Word. It kept stalling out and it crashed on me. And when it crashed, it didn't save the last like 5 minutes worth of work. Thank you for pointing that out. So I at least want to rewrite what I had up there. Sorry about that. Dang it. Dang it, dang it, dang it, technology. All right, we got to roll with the punches though. But we said if, I can type this. The special memo I gave was if the inside of an inverse sine is negative, the answer will simply have a negative answer. That related to D, which was inverse sine of -1/2. Sorry, like I said, I'm just going to write and talk this really quickly. So we said this was the same as saying find theta such that, or so, the sine of theta is equal to -1/2, but only consider quadrants 1 and 4 because of the inverse sine only being valid in quadrant 1 and 4. Well, that means we need a reference angle because anything with negatives means reference angles are involved. So reference angle. The opposite would be 1, the hypotenuse would be 2, which makes the square root of 3, which the angle opposite of 1 has to be 30 degrees, which is pi over 6. So if theta prime is pi over 6, based on that little shortcut sheet I gave you, if you remember it, so that means theta has to be negative pi over 6. Or 11 pi over 6, but that answer is not valid. And that's because we're in quadrant 4 by a smart trig class. Sine is negative in quadrants 3 and 4. Okay, so that was reiteration. Sorry for that. Thank you for pointing that out to the student that did to me. E is actually inverse cosine of square root of 2 over 2. Now, first of all, I'm going to say that this is the same as finding the inverse cosine of 1 over square root of 2. This is something that you've got to get used to understanding and seeing, because we don't memorize this triangle with square root of 2 and 2. We memorize it with a 1, a 2, and a square root of 3, or not this triangle, but the 45, 45, 90 in particular. So you need to remember that these two numbers are the same thing, and we end up having to rationalize denominators so much that I hope that you do. Pattern recognition is important. So that means we are really trying to find an angle such that the cosine of said angle is equal to 1 over square root of 2, or 2 over square root of 2. I'm sorry, square root of 2 over 2. The black version or the blue version, whichever you like, but I prefer this one. But it can only be, we can only consider quadrant 3 and 4. What am I saying? What am I saying? I'm thinking one step ahead. It's quadrant 1 and 2. It can't be in quadrant 3 or 4. That was because, I'm not scrolling, there we go. The inverse cosine is only valid between 0 and pi. 0 and pi are quadrants 1 and 2. 0 to 90 is 1, 90 to 180 is 2. So inverse cosine is only valid in quadrants 1 and 2. Now, when you're dealing with the positives, the cool thing is it won't matter whether it's an inverse sine or inverse cosine. You'll get lucky because both of them, any positives go for quadrant 1, but the negatives for the inverse sine go to quadrant 4, not 3, where it would also be valid the other way, the simpler way. Inverse cosine is positive in quadrant 1 and 4, so negative in 2 and 3, but you only consider 2, not 3, again, for the reasons we've discussed. We had to trim it up. This is only valid from quadrant 1 to 2. So positive answers, you use the angle in quadrant 1. Negative, it depends if it was inverse sine or inverse cosine. How can you remember that? So is it just blind memorization of this fact? Doesn't have to be. What you can do if you're stuck, and this is exactly how I do it, and I'm telling you your teacher does not just blindly memorize factoids like this. I hardly ever do things that way. I rationalize them. So if I have a test, what I do is I draw my sine and cosine graphs and I figure out how they're supposed to be chopped up on the fly. I do my horizontal lines and I chop them up. So this, if I was the student taking the test, I would have literally done this stuff to figure out, all right, well, here's my sine wave, but how do I need to chop this up to make sure it's invertible? Well, this is how. So that tells me I got to use quadrant 4 and quadrant 1, because we're going from negative pi over 2 to pi over 2. And then I draw my cosine wave, starting at a height of 1 and waving, waving, waving. And I go, well, no, I got to chop this up, and then this is how I chop it up. So I only use quadrants 1 and quadrant 2. That's what I would do if I were the student, instead of just blind, blatant memorization. Do you have to do it that way? No, that's up to you. All right, back to the point, back to the problem. So we're trying to find an angle such that the cosine is 1 over square root of 2. Well, we could use our board sheet thing, but I'll just redraw the triangle real quick. Now this is positive, so it is the actual angle, not a reference angle. The adjacent is 1, the hypotenuse is the square root of 2. Well, this is the 1 square root of 2 triangle, which says that the angle has to be 45 degrees, which is pi over 4. That's the answer. No negatives, no problems. If the original arguments were positive, with inverse trig functions, the answer goes in quadrant 1. Easy peasy. Let's do one more. Switch back our color to black, though. Draw black. Here we go. F. Inverse cosine of negative square root of 2 over 2. So we're trying to find an angle. Now this square root of 2 over 2, same thing as last time. So I prefer to say this is the same as saying the inverse cosine of negative 1 over square root of 2, because that'll make it easier for me to associate the correct triangle with it. All right, so what we're doing is finding an angle such that, so the cosine of said angle is negative 1 over square root of 2, but we only consider quadrants. Which ones is it, 1 and 4 or 1 and 2? Now you might be wondering, how do you know it's 1 and 4 or 1 and 2? Why not quadrant 3? Quadrant 3 is never, ever, 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 ever used for inverse trig functions. Because you need this smooth, continuous graph for your inverse trig functions. So you only end up ever using 2 quadrants. So to do this, it's quadrant 4 and 1. To do this, it's quadrants 1 and 2. The only way you could use quadrant 3 is if you were going in quadrants 4 and 3, which you would never ever do. You always want to use quadrant 1 and then whatever is next to it. So quadrant 4 is next to it, quadrant 2 is next to it. So it's one of those. Don't ever put it in quadrant 3 for inverse trig functions. For cosine, well, cosine, so this is the way I do it on a test. All right, what's cosine wave look like? We start at a height of 1 and we do, that was poorly drawn. We do this and it goes forever in each direction, where we know that this would be pi. Okay, well, this is going to fail the horizontal line test, so you have to trim it up, and you end up trimming it between here and here to make sure that there's no overlap. If you keep going, you'd fail the horizontal line test. So that tells me I'm between 0 and pi, and then I know, hey, I'm only using quadrants 1, 2, not 1 and 4. All right, so we'll draw up our triangle, but because there was a negative involved, that makes this a reference angle. The opposite, the adjacent should be the 1, the hypotenuse, the square root of 2. It's the 1 square root of 2 triangle again, which says that theta prime is pi over 4. But we need to put this in quadrant 2. So we draw the angle in quadrant 2. Here's our pi over 4, that's our reference angle, which means we're trying to figure out this angle. This is our true theta, which would be pi minus pi over 4, or 180 minus 45 degrees, whichever way you need to do it. So theta would be equal to pi minus pi over 4, which is 4 pi over 4 minus pi over 4, which is 3 pi over 4. Just making that minus a little clearer. There we go. So that's our answer. Theta equals 3 pi over 4. So I gave you a helpful little memo earlier for the sine, technically last class. If the inside of an inverse sine is negative, the answer will simply have a negative answer. That's not the way it works for the cosine, though. So that little memo here is the inside of an inverse cosine is negative. The answer is in quadrant 2, and theta should be equal to, I'm going to write that part out. Pi minus the reference angle. That's the little shortcut sheet, whatever you want to call it, if you like to use that. Okay, so those are our inverse sines and cosines. Now we're not done with those. We will come back to those later in this section when we make things a little more complicated. You're probably wondering, how in the world are you going to do that? Isn't this bad enough? Well, we're going to start stuffing one thing inside of another thing. We're going to start doing composite trig functions. Oh boy. But you have to be careful. You can't just stuff a sine inside of a sine. You can put sines inside of inverse and inverses inside of sines, but you can't do an inverse in an inverse or a regular in a regular. You'll see what I mean later. For now, let's get to talking about the tangent. Y equals, and I'm going to skip the graphical rationalization of this one, but y equals inverse tangent, sorry. Y equals regular tangent of x must be restricted to negative pi over 2 comma pi over 2. In parentheses, though, to be invertible. I have 2 twice, don't I? There we go. It still doesn't like it, whatever. Ignore, where's ignore? Where's ignore? It just went away on its own. I love technology. All right, so again, skipping the graphical part just in the interest of time. Actually, I'm lying. I'm going to show it below. I'm lying. Sorry, hold on. Give me 30 seconds. All right, sorry, I dropped my notes for today's class, not for this part. So regular tangent graph is what we're trying to draw. So remember, it looked like a cubic, and it had asymptotes between negative pi over 2 and pi over 2. So if we drew this thing forever and ever and ever, it would just kind of look like this, and then another one, and another one. And you can see that this would fail the horizontal line test miserably. So you got to trim it down. So what you do is you just use this. That section right there would be the perfect trimming, because it will pass the horizontal line test if you ignore my poor artistic ability where it humped over right there. So that's the reasoning that we restrict the tangent to negative pi over 2 to pi over 2. This is the same restriction. Actually, let me be a little more specific. This is almost the same restriction as sine. This is the restriction for tangent, where negative pi over 2 to pi over 2, but surrounded in parentheses. Let's look at the restriction for sine, though. Sine was restricted to negative pi over 2 to pi over 2, but it had brackets. It had brackets around them instead of parentheses. Why is that? Why did we have brackets for that one? Well, because these points were included. We'll have parentheses for this one because this negative pi over 2 and this positive pi over 2 are asymptotes and have to be excluded. That's why we use parentheses there, due to the asymptotes, the asymptotes. That is the only difference between this and a sine. So sine and tangent are close to each other at least. Cosine's the odd man out that goes from 0 to pi. Sine and cosine use brackets, tangent use parentheses because of asymptotes. All right, so with that in mind, y equals, I'll write it out. Y equals inverse tangent of x has a domain of negative infinity to infinity and a range equal to negative pi over 2 to pi over 2. Remember, regular trig function's domain becomes the range of the inverse function. Regular function domain becomes the range. Then the regular function's range becomes the domain. I never wrote the regular function's range, but you can see it. It goes up forever, it goes down forever. So this right here, excuse me, was the range of just a regular y equals tan x, not an inverse function. So that was the range of tan, so it's the domain of inverse tan. And then I'm going to go ahead and make the memo for the, what quadrant is it in if there's a negative argument. If the inside of an inverse tan is negative, then the angle is simply negative. Notice this is the same as inverse sine. Argument. Literally the same argument as the inverse sine. So inverse cosine is kind of on its own island. I really don't do a lot of inverse tan functions. They're not nearly as interesting. So let's just do one of them. What example are we up to? 2? It's got to be 2. Yes. So example 2, evaluate. This is just going to be y equals inverse tangent of -1. Now remember, when you're looking at inverse trig functions, the inside is supposed to be the ratio of opposites, adjacents, and hypotenuses. For a tangent, that should be the opposite over the adjacent. That's what the inside should be. It should be an opposite over adjacent. But it's not written as a fraction, it's written as a whole number. So what you might want to just say is this is the same as y equals inverse tangent of -1/1. That helps a lot of people. So what we're trying to do is we're trying to find an angle so that or such that the tangent of said angle is going to be -1/1. Inputs and outputs are swapping when you go to the regular function. But we only, looks like a bot, but we only consider definitely quadrant 1, but what's the other one? Is it 2 or 4? Is it 2 or 4? Well, remember, tangent had that this look, and we were asymptoted, and we had to go to the left, so that meant we're going between negative pi over 2 and pi over 2, which is quadrant 1 and 4. Why did I write 2? 1 and 4. All right, so let's set up our, because this is negative 1 over 1, let's set up a reference triangle. So this will be our theta prime. The opposite will be the 1, the adjacent will be the 1. This will be a square root of 2, and that instantly says that theta prime is pi over 4. Because you have memorized that triangle, or you've just memorized blatantly the fact that the tangent of 45 degrees is 1 over 1. It's up to you how you're doing the things, but I've given you multiple ways to do them. All right, so since the angle is supposed to be negative because of that, that just says theta is equal to negative pi over 4, based on that memo I mentioned earlier. If you don't believe me, if you don't trust the little memo right here, what you do is you draw this angle, but in quadrant 4. And when you draw pi over 4 this way, you just rotate clockwise to get negative pi over 4. Remember, you don't want to go counterclockwise because that would give you a, was that 7 pi over 4, which is outside of the range. So that's just a clockwise rotation of the same angle. All right, let's keep bumping this down. Sure. Now, what we're going to start studying for the final bit of the section, composite trig functions. Composite means one inside of the other. So a sine inside of an inverse cosine, or an inverse tangent inside of a cosine, or a secant inside of an inverse secant, or a sine inside of an inverse sine, or an inverse sine inside of a sine. But the trick there, and it's not a trick that you have to know, you can only be given this style problem. You can't be asked what's the cosine of pi or something like that. It doesn't work. You can't take the cosine of something, because remember, when you spit out the cosine of an angle, you're getting a length, a ratio of lengths. And then if you try and take the cosine of a ratio of lengths, that literally doesn't exist. You can only take the cosine of an angle. So you will only see problems where, for these composite functions, one will be an inverse and the other will not. The inverse could be inside or it could be outside. Doesn't matter. They could be the same type of trig function or they could be different. It doesn't matter. But when they are the same type of trig function, sometimes you get some really easy cases, and that's what we're about to detail. The angle is part of the range of the inverse function. Then you can say, I almost want this to go down the line, that the inverse sine of a regular sine of an angle is equal to the angle. Or, same thing, if the angle is part of the range of the inverse function, then you can say the inverse cosine of the cosine of an angle is just equal to the angle. Or, if you have, I think you're know where I'm going with this, the inverse tangent of the tangent of an angle, that would be the angle. The idea here is that inverse sine and sine cancel, inverse cosine and cosine cancel, inverse tangent and tangent cancel. In the same way that if you have x plus 5 equals a number, you subtract 5 on both sides to cancel. Addition and subtraction are inverses of each other. Multiplication and division are inverses of each other, so they cancel each other. Square roots and squares are inverses of each other, so they cancel. A function and the inverse function are literally inverses of each other, so they cancel. And in all those ideas, when you cancel, you're left with the base argument. With trig functions, it's the angle. But there's a special condition for this. and that is if the angle is part of the range of the inverse function. This is not always the case. So inverse functions only work if you're actually in the appropriate values. So if you're dealing with an inverse sine, you're only good with values in quadrants 1 and 4, and the quadrants in 4 have to be just the negative versions of quadrant 1. If you're dealing with inverse cosine, you're only valid in quadrant 1 and 2. My point being, if I asked you the inverse sine of something where the angle is in quadrant 3, you couldn't just say they cancel, you would actually have to work from inside out. So that is a very important detail. Yes, in general, up to this point, all inverses and regular things have canceled with each other. Addition and subtraction canceled, multiplication and division canceled, square roots and squares canceled. But in trigonometry, because we had to narrow the windows so much to half of a circle, not even a full circle, that means that these two don't always just cancel each other out. Sometimes the angle that's the answer would be different from the angle that was in the argument. So you have to pay attention. Oops. Type, please. Thank you. So if this is not the case, why did my font size changed? Why did my font size change? Either way, if this is not the case, you work inside out. Just like with composite functions, because that's literally what these are. So if the angle is not inside of the range, you have to work them inside out. Also, if these functions don't match, by match, I'm putting it in quotes because they're never going to literally match. I mean, you have a tangent and an inverse tangent, or a sine and an inverse sine. What I'm saying is if you add an inverse cosine of a sine, so if they don't match, you must work inside out as well. So that'll bring us to example 3. Evaluate. And for A, we're going to have the inverse sine of the sine of pi over 4. Now you might be thinking, well, could you do the sine of the inverse sine of pi over 4? The answer is no. You cannot do the sine of the inverse sine of pi over 4 because with inverse trig functions, the inside argument must be ratios of opposites and adjacents, something like a half or square root of 3 over 2. So no, you can't just willy-nilly flip these and leave the pi over 4. It would have to go in this order. If I wanted to do a sine of an inverse sine, it would be something like, I'm not actually doing this, inverse sine of maybe a half. We'll be doing problems like this in example 4. Don't worry. So when it's an angle, it has to be sine of an angle. Okay, so inverse sine of pi over 4. Well, these two are the quote same, they match, they're inverses of each other, which means maybe we'll have this special case. If the angle is part of the range, then we can just say the whole thing would be equal to pi over 4. Don't assume though, make sure it's right. So pi over 4 is in which quadrant? Quadrant 1, which is valid for inverse sine. Inverse sine is valid in quadrants 1 and 4. So this is fine. So we can just take that quick little cheat and say, so the answer is equal to the argument of pi over 4. Easy peasy. Spoilers, B might not be the same. Let's do the inverse sine of the sine of pi. So pi is between quadrant 2 and 3. Now, if we were talking about pi over 2 is between quadrant 1 and 2, but it is the edge of where inverse sine is valid. It's valid up to pi over 2, so that'd be fine. Pi is way outside of that range. This is not valid for inverse sine. It wouldn't even be valid. I'm sorry, I was about to say something wrong. This would be valid for inverse cosine. We can go from 0 to pi for inverse cosine, but we go between negative pi over 2 to pi over 2 for inverse sine. So if I switch these sines to cosines, the answer would be pi. But it's not. They're sines. We're not in that valid window, which means we have to work inside out. So the first thing we do is find out what is the sine of pi. Just focusing on the inside. What is the sine of pi? Well, that's a quadrantal, so you go to your unit circle. Pi is 180 degrees. That point, I'm going to erase this after I draw it up. 180 degrees would be this point right here, which is negative 1, 0. The sine means we're taking the y value, so we're taking the 0, which is 0. So the sine of pi is equal to 0. So sine inverse of sine of pi, I'm just writing blue so you can see the direct substitution. This will now be the inverse sine of 0. Now this 0 is not an angle. This is not 0 radians. This is the ratio of 0 over literally any number. So what you're asking here is, we're trying to find the inverse sine of 0. So what we're saying is, find an angle so that the sine of that angle is equal to 0, but we're only between quadrants 1 and 4, up to their borders. There are two values of which the sine of an angle is 0. If you go to that unit circle, let me pull that up now. I don't want to have to keep redrawing it. That's the wrong class. 162, board cheat sheet. So here's our unit circle. So we're trying to find where is the sine equal to 0. Sine is the y value, so we're looking for y values that are 0. Here is a y value that's 0, and here is a y value that's 0. But we've already talked about how 180 degrees is outside of what we're supposed to be looking for. For an inverse sine, we're not looking at this side at all. It doesn't exist for an inverse sine. We're only looking at this half circle. So that means 0 degrees or 0 radians is the only angle. There's not two answers, and that would be the answer. So theta equals 0. So that means the inverse sine of the sine of pi is equal to 0. That's the answer. It was not equal to pi. Again, because pi was outside of the window. Now anybody be saying, well, since it was outside of the window for inverse sine, you don't even do it. Well, it doesn't matter because inside of here, we're not even looking at the inverse sine. Pi is perfectly fine for a regular sine. So that's not an issue until we go outside of it. But outside of it, we've already turned that into ratios of sides. So it's irrelevant where we started. This is one of my favorite types of problems because it really emphasizes that while inverse functions generally cancel each other out, there's special types of inverse functions with very, very narrow windows, which means they don't always just cancel each other out, so you got to work inside out anyways. It's annoying, it will frustrate you, but it's important. All right, last set of examples for the section. Example 4, evaluate. A. Now let's start mixing them up. So for these 4 problems, I'm going to switch the order of inverse and regular function, but it doesn't have to be that way. I can still ask what's the inverse cosine of the sine of pi, or what's the inverse tangent of the sine of pi over 4. I can certainly do that. And again, you're just working inside out. That's the core idea of these problems. If they don't match, work inside out. Do the inside problem on its own, then do the outside problem with the new information that you have. So for A, we're going to do the sine of the inverse tangent of 7/24. sine of the inverse tangent of 7/24. First thing you might think is, we haven't dealt with any triangles with ratios of 7 to 24. How am I supposed to know if this is 30 degrees or 45 degrees or 60 degrees? Well, guess what? It's neither of them, or none of them, since it's three options. And it's definitely not a quadrantal. So then you're going to go, well, Mr. Beckner, you never told me to memorize all these other angles that have ratios of opposites and hypotenuses of 7/24. Here's the cool thing. I didn't ask you to do that because you don't have to do that. It has nothing to do with this problem. You're never going to find the angle of this. You're just going to use the angle, build your own right triangle, and find the answer from there. So you'll just have a theta written somewhere. You'll never actually determine it. I never asked for an angle. I asked for the sine of an angle. This right here, wrong color. This right here is the angle. So we just want some sine of theta where the theta is bound by these values. So again, the first thing you need to do is find out what is the inverse tangent of 7/24. It's equal to some angle. So we're finding some angle so that the tangent of it is equal to 7/24. Again, if you don't need to do this rewrite, that's up to you. I know not everybody does. I personally don't, but I've done this a lot. I definitely did it at first. All right, well, how do we find this? Well, that's an opposite over an adjacent because SOHCAHTOA. That's another thing, if you don't memorize, you're gonna regret it all semester. So let's just draw a right triangle where our angle's here. TOA, T-O-A, so the opposite is the 7, the adjacent is the 24. And then this would be our hypotenuse. We can label it C if we like. And then we can find that based on Pythagorean. So we know that C is going to be the square root of the A squared plus B squared. I'm not going to rearrange the formula for the 10 millionth time. So that'd be 7 squared plus 24 squared. Spoiler alert, when you do all that arithmetic, I'm going to entrust you to do it. You're going to get 25. But 7 squared is 49. 24 squared is what's that, 576. And then 576 plus 49 is 625. And the square root of 625 is 25. So that tells you what your hypotenuse is. So now if you really wanted, you can redraw the triangle, 24, 7, 25. Ooh, it's got nice pretty whole numbers. There aren't a lot of triangles built that way. We have the 3, 4, 5 triangle. We have the 5, 12, 13 triangle. There's the 7, 24, 25 triangle. There aren't, I think there's only one more, and I don't know it off the top of my head, where it's only using single and double digit numbers, and they're all whole. It's a pretty rare instance. Yes, there are multiples of those 3 base triangles, but they all are just multiples. Like 3, 4, 5 means there's also a 4, 6. I'm sorry, I said that wrong. 3, 4, 5 means there's also a 6, 8, 10. You can just double the values or triple the values or quadruple the values. All right, so while we can't actually find out the angle, we can't find theta literally without a calculator. I would need a calculator to find out this angle, which I'm going to start showing that, I guess, after this problem. I was going to wait till the last 4, but it's relevant now. We can't find the angle, but that's okay. We don't care. Just call it theta. So the theta is bound to the fact that its inverse tangent is 7/24. So the sine of inverse tangent of 7/24 is the same thing as finding the sine of what we're calling theta, where theta is based on this right triangle, this one more specifically. So the sine of theta just says to go to this right triangle and do its opposite over its hypotenuse. So this would be equal to, the opposite is 7, the hypotenuse is 25, so the answer is 7/25. That's it. That's an ugly 5. The sine of that angle is 7/25 based on the triangle we drew up. So we're just asking for the sine of the angle, which was the sine of the inverse tangent. Again, don't try and look at this all at once. Don't look at this all at once. It's a terrible idea. Focus your field of vision to just the inside, which for an inverse trig function, very often you're drawing up a little triangle for that, even if the numbers aren't numbers you've seen before. And then when you do the outer trig function, you're generally just referring to that triangle. If we did this the other way, if we were doing the tangent of an inverse sine, and again, this would now be an angle I'd have to write. I'd actually have to write an angle, which means I'd have to use angles that we're used to, which is why we're much more limited, and generally the problems are like this, which is why I do them this way and not the other way. Okay. B, cosine of the inverse sine of a half. How much time we got? About 15 minutes. Should be just enough time to finish this section. I hope. Oh no, I said I was going to do something, didn't I? Before we do that, calculator. So this was an issue that would have come up for a word problem or two. And yeah, let's get radians for now. That I said I was going to come back and approach, and I was going to do it at the end of this section, but I might not have time today now that I'm running short. Shoot. Either way. So the inverse tangent of 7/24, we literally never said what it was. We just said that it means we're forced to this right triangle. That would tell us everything about the inverse tangent of 7/24. If you wanted to find that in a calculator, look where my mouse is, if you can see that. Here's the tan button on a TI-83. The inverse trig functions are usually on the same button, and you hit second and then that to get to it. So I could do second tangent of 7 divided by 24. And this answer would be in radians because I'm in radian mode. So in radians, that's 0.283, and that means nothing to you probably. So let's change our mode to degrees just so we have a better grasp on it. And let's do the inverse tangent of 7/24 again. And it says it's about 16 degrees, 16.3 degrees, rounded to the nearest tenth. Okay. Well, that's cool. So it's about 16.3 degrees, and then the sine of that turns out to be 7/25. But if we did it this way and then try to do it, if you do this, the sine of the inverse tangent of 7/24, so if you just plug this in a calculator, you get 0.28. Okay. But why is it 0.28? And if you wrote 0.28, I think my math lab wouldn't even like that, because it would want this as a fraction since it could get converted, and typically we use fractions, not decimals, when we're talking about ratios of opposites, adjacents, and hypotenuses. So don't think your calculator is going to do everything for you. First of all, this is a no calculator test. You're not even supposed to be using this. Second of all, inverse trig functions in calculators are very wacky when you're using them, because the calculators have the issue of they're not always sure about the quadrants. So you might do a sine of an inverse trig function and you get something and it's supposed to be the negative of that. Or you get a negative and you were actually supposed to have the positive of it. So you just have to be careful. Inverse sine of the sine of pi. Make sure our mode's in radians again since I did it that way. See, that's right, but there's always a possibility that it's wrong, and I'm not going to show any right now, but please trust me that they can be wrong if you're dealing with anything that might have quadrant 2, 3, or 4 involved. All right, now on to B. Cosine of inverse sine of a half. So the first thing you want to do is you just argue the inside, and the inside's supposed to be an angle. So first, we say that the inverse sine of a half is equal to theta, or x, or whatever letter you like. It doesn't matter. I just like theta. So that means we're finding theta so that the sine of theta is equal to a half. Well, that's a very well-known triangle, but of course we're restricted to the quadrants. We're dealing with inverse sines, so quadrants 1 and 4 only, but this is positive, so that won't be an issue. When you draw your little triangle, here's your angle, 1, 2, square root of 3, which says that your angle is actually pi over 6, but we don't actually need this. We didn't need it in the last problem. And what I mean by we don't need is we don't need to know the actual angle. Even though, yes, it is pi over 6, I don't actually need to know that. I can still just call it theta. So I can go for the second phase. And we're doing the cosine of what I've called theta. I don't even need this. I can completely ignore the fact that it's pi over 6, and I could just go, oh, well, cosine is the adjacent over the hypotenuse, so it's square root of 3 over 2. I didn't need to know that it was pi over 6 this time. It's very rare you don't need to know that. And that's by, again, this triangle. Again, did not actually need to know that fact. It's good to know, but I didn't need it. So that says the cosine of the inverse sine of a half is equal to square root of 3 over 2. That's the answer. C. The secant, of inverse sine, right? Yes. Of negative 1/2. Negatives, secants and negatives. Oh boy. First thing we do is we're just considering the inside. We're trying to find the sine, the inverse sine of negative 1/2. Inverse sines, inverse trig functions are angles, so let's call it an angle. Which really means we're trying to find an angle such that, or so, the sine of that angle is negative 1/2, and we're limited to quadrants 1 and 4. We'll have to be in quadrant 4 because it's negative. Oh, but sine is negative in quadrant 3. Doesn't matter. Inverse sine is not valid in quadrant 3. No inverse trig function is valid in quadrant 3. All right, so that means we can just draw up a reference triangle with an opposite of 1, a hypotenuse of 2, and that means the adjacent square root of 3 again, which says our reference angle is pi over 6. Again, I don't actually need to know that. But it would be tougher ultimately without knowing it for a couple of reasons. If the reference angle is pi over 6, that means the actual angle is negative pi over 6. And that's why I'm going to say it's slightly more important, not necessarily to say that it's pi over 6, but the fact that it is negative, which puts us in quadrant 4. Three exclamation marks, because we're going to be taking the secant of something in quadrant 4, which means we could screw up the plus or minus aspect if we're not paying attention to those great details. So now, second of all, we're doing the secant of what we've decided to call theta. Yes, it's negative pi over 6, but really we're just using this triangle and the fact that it's located in quadrant 4. I didn't need to say all of this. I just know it's in quadrant 4, which means that angle would have been negative. Okay. So the secant of that angle, well, secant is 1 over cosine, if you prefer it that way. If you don't, then don't change it. Secant is 1 over cosine. Cosecant is 1 over sine. So cosine is adjacent over hypotenuse, which means secant is hypotenuse over adjacent. So we're doing hypotenuse over adjacent, which is 2 over square root of 3. So this would be equal to plus or minus 2 over square root of 3. I've got the plus or minus because we're in quadrant 4. We have to make sure we get this right. In quadrant 4, secant, which relates to cosine. All right, quadrant 4 means we're going right. Cosine is an x value, which means we're going right, which means it's positive. If this had been a cosecant, which would relate to sine, quadrant 4, sine's negative, so we'd choose the negative instead. So the secant of this angle is equal to negative 2 over square root of 3. But you're going to be slightly annoyed. There's one final detail we have to account for. We got to rationalize the denominator, multiply top and bottom by square root of 3, giving us a final answer of negative 2 square root of 3 over 3. Why did I say negative? I said to choose the positive, and then I wrote a negative because I got so focused on that sign, excuse me. Erase the negative. Erase, you silly computer. Erase the negative. We chose the plus. I said it, I wrote it. Be consistent. 2 square root of 3 over 3 is the answer. This is one that a lot of people would think the answer is negative because this inverse sine had a negative. Oh, so just give the secant a negative. Nope. Because sine is negative in quadrants 3 and 4, but secant is negative in quadrants 2 and 3. These subtle details will make or break you. All right, D, last one. Tangent of the inverse cosine of negative 3 over 7. Again, the first thing you do, focus on the inside. Inverse cosine of negative 3/7. Sorry if my audio is a little unstable. It just told me my internet connection's unstable. Remember, recordings are always fine. So if this is buggy, go back and watch this last part later. All right, so remember, we're calling this an angle, which means we're trying to find an angle so that the cosine of the angle is equal to negative 3/7. But we're restricted to quadrants 1 and 2. If it's negative, it will be in quadrant 2. Remember, we're restricted to quadrant 1 and 2 because we talked about an inverse trig function. If I never mention inverse trig functions, and I don't just blatantly say there's restrictions, then there's no restrictions. All right, 3 and 7, we definitely haven't made a triangle out of that, so let's make a triangle out of that. Because we're in quadrant 2, I'm going to call this a reference angle. Cosine is adjacent, so here's the 3 over hypotenuse, here's the 7. Let's call this B, and we can find it based on Pythagorean. B, again, you can rearrange the formula on your own, ends up being the square root of 7 squared minus 3 squared, which is 49 minus 9, which is the square root of 40, which would be the square root of 4 times 10, which would be 2 square roots of 10, when you reduce it as much as possible. That triangle is really the 3, 2 square root of 10, 7 triangle. I have no idea what that angle is. You will have no idea what that angle is. Don't put it in your calculator, because I don't care what that angle is. We're just going to be using this to build the tangent. But remember, this is theta prime. We're really supposed to be noting that this is in quadrant 2. Because the cosine was negative, that means we're going left, either quadrant 2 or 3, but inverse cosine is not valid in quadrant 3. So make sure you're considering that when you do your tangent. So now, oops. Now what we're doing, or second, now is probably a bad word choice for later, now and later. All right, we've got the tangent of the angle. The angle is based on that triangle. The tangent would be opposite over adjacent. So it's plus or minus 2 square root of 10 over 3. Since we're in quadrant 2, tangent is negative. So we choose the negative one. So the tangent of our angle is negative 2 square root of 10 over 3, and that is our answer. That's what the original problem is equal to. So many students will forget this negative, and the whole thing's wrong because of that. And then you go, hey, Mr. Beckner, check me for partial credit on this question. And I go, you didn't show your work, no credit. If you did show your work, then I'll go, okay, yeah, you'll get 4 to 5 points or 3 to 5 points, some tangible, pun intended, amount of points. All right, that technically closes the section, but I want to do one quick thing that I kept mentioning last class and today. I have just enough time. Previous word problems, IOUS. And 5.2, 5.3 might have been something like this. Bob is doing physical therapy. And he's laying flat on the ground and he's trying to lay his arms flat. So he takes his arms, which are initially pointing straight up. He's holding a bar and he's using one of his arms to bend behind his head. and he manages to drop his arms as low as possible. He knows his arm is 2 feet long. And his friend manages to measure the lowest height he can achieve at 0.3 feet. What angle does his arm form against the ground? So here's what I'm saying. This is the image, and they basically draw these images up for you anyway. So he's pretty low at this point. So this right here is his arm. This is the, like, let's say it's not right at your shoulder, it's in your armpit, but that pivot point might be a little just off center. Don't worry about it. But that's his arm, which we said was 2 feet long. So he's got a 2 foot long arm. Then he's got a friend who manages to measure this distance, the vertical distance from where his hand is. So this right here is his hand, or the tip of his finger. Hand, finger, whatever. And then this was 0.3 feet. I didn't want to do it in inches because I don't feel like converting units. And they say, what angle does his arm form against the ground? So that's the angle right here. We don't know this horizontal distance. Guess what? We don't need to know this horizontal distance. Yes, we could find it by Pythagorean, but we don't need it. So I did some word problems like this previously, and we said, you want to try and use a trig function where you're going to use 2 of those quantities, or if one of these was unknown, then you try and use at least one of them. So we know the opposite, and we know the hypotenuse. What trig functions use opposite and hypotenuse? Sine and cosecant. Let's not use cosecant because it's the one that's, goofier. So we're going to use sine. So we would say the sine of that angle is equal to the opposite of 0.3 feet over the hypotenuse of 2 feet. Well, guess what? This is exactly like an inverse trig function. So this would be the same as finding the inverse sine of 0.3 over 2. That would be equal to our angle. We just spent the entire class going from the blue to the black. Now we're going from black to blue. Well, this is an application, so we're definitely just putting this in a calculator. They're all positive because we're not going to deal with negative links in terms of geometry. So we pull out our calculator. Now, if you want the angle in degrees, let's check our mode. We are in radians currently, so let's go to degrees. This would probably be a little more relatable. Pay attention to what my math lab wants the answers format as. If it wants radians, leave it in radians. So we're going to go inverse sine, so second sine, and then we're going to do 0.3 divided by 2. And when we hit enter, we get 8.6 rounded to the nearest 10th degrees. So that says theta is equal to 8.6 degrees. So that's actually pretty low. That's pretty good in the physical therapy process. It's not always use an inverse sine or a sine. If I had given you the opposite and the adjacent, you'd use a tangent. If I had given you the adjacent and the hypotenuse, you'd use a cosine. Don't use the other 3 because there are no inverse buttons for the other 3. There's only inverse buttons for sine, cosine, and tangent. So again, that was in 5.2 or 5.3. If anyone needs that homework opened back up to achieve those problems now that you've seen it, again, you had to view an example, so you probably already saw this if you're good students. But if you did need a little more practice with just this, let me know and I'll go back and give you another day or 2. Email me. If I have 5 people email me, then I'll do it for everyone. But email me today. Don't do this in a week. I'm not going to give you an extension a week later. All right, that finishes 5.7 just in the nick of time. So that homework is due in a week. Again, that is the 7th of October. I hope that we can complete the last section next class, which means that the test will be that range, but I don't want to confirm that until, you guessed it, next class. So have a good one, have a good weekend, study hard, work hard, put your 6 hours a week in, and email me with any questions. Take care, everybody.